on methods for comparative effectiveness research. The plan is to have John Brooks speak for 30 to 40 minutes, and after that we have discussions. You might have comments that you want to type into your WebEx, and then we read it out loud for you, or we unmute all the people on the phone, and then you can just speak, and we will hear you. I also want to mention that we have a set of very interesting speakers and topics lined up after this. We have a topic on adjusting for non-adherence during follow-up with Darren Toe. Selecting between propensity scores and disease risk scores, which also fits nicely to today's topic. So as you can see in this entire series, we're moving more and more into the analytic issues now that we have dealt with the design issues predominantly at the beginning of this seminar. So today's speaker it's a great pleasure to announce Professor John Brooks, whom we all know well from the University of Iowa. And John has a track record of not shying away from the difficult questions. He's published a series of papers on instrumental variables and identifiability. And of course, this is all intertwined with propensity scores. So I'm looking very much forward to your presentation, John, and an interesting discussion, I hope. So hand over to you, John.
Sebastian, appreciate it, and thanks for the opportunity to let our simulation research on propensity scores that comes from a couple of health economists here. My colleague here is Robert Osfeld from Texas A&M University, and that's for Bob and I, and probably for a lot of health economists out there, that we stress the importance using choice theory and when trying to interpret treatment effect estimates from observational data, that in some respects, and it's not always true, oftentimes there isn't kind of an atheoretical bent to propensity scores methods that can kind of, and it has, stuck in the economist's craw in some respects. And so, you guys, not economists say, why are these guys so grumpy about this? And but we don't really know. I mean, in some respects, we did have an uneasiness about the ability for propensity scores to do what people suggest that they can do, but we never I couldn't find a paper to suggest this sort of uneasiness, and so we got together, and Bob and I, and we, as I'll talk about in a few minutes, we just simply adapted a model that we had for other purposes, and that was one of the papers that was sent around to you guys, and where we tried to just get at this question of the balancing properties of propensity score methods, both in terms of how propensity score methods balance the measured covariates, which has been described quite a bit in research, but also with simulation methods, trying to ask questions of how propensity score methods balance the unmeasured covariates. And to be frank, we found results that really surprised us here. And the results I'll be showing you in these slides is kind of a summary of the results of all the different model specifications we tried, and we couldn't in some respects, shake the result that we found that I'm going to be presenting to you guys here today. And so, my last bullet and the last slide here is a challenge to try to anybody else to try to come up with a different type of simulation model that shows a counter to our results, or a different way of approaching this. So we're open to anything, and once again, realize that we found some results that we simply couldn't make go away. We couldn't specify the model differently and see different results. So, moving through slides. Wait a second. Okay. Sorry, folks. Here we go. So, researchers have called, and there's a couple of key papers in this regard, have called applying principles from randomized experiments when estimating treatment effects and outcomes from observational studies. And propensity score methods have often been offered as a means to approach this randomized experiment ideal. And the treatment effect identification, the ability to identify a treatment effect using propensity score methods, requires the assumption of an ignorable treatment assignment. And this goes way back to the papers by Rosenbaum and Ruman back in 1983, where this idea of ignorable was described. And I've tried to write down what I feel, what I meant by something being ignorable or ignorable treatment assignment, but I think it comes down to, after conditioning on measured factors that affect treatment assignment, the remaining factors affecting treatment assignment are either have no effect on outcome, which economists would argue would require theory to motivate the idea that what's unmeasured has no effect on outcome. You need a theory to describe why that may be true. Or after conditioning measured factors, the remaining factors affecting treatment assignment are balanced between treatment and control groups after conditioning on the measured factors. And if you choose number 2 as your basis for treatment identification, you really don't need a lot of theory to require that. And there was an interesting paper that I found in the Clinical of Epi by Shaw and colleagues from 2005 that went back and did a review of the literature on propensity score methods and found that a lot of people base their identification on, if you balance the measured, that's going to imply balance, hopefully will imply balance on the unmeasured, and relying on number 1 here of theory. But not everybody, but they found a preponderance of folks that were relying on this balanced on measured, implied balanced on the unmeasured. So I just went out, and here's an example of a chart that I found in a paper that was in the International Journal of Cardiology from 2010, where authors, compared treated people based upon measured characteristics before applying propensity scores that they used to match patients with, and then they matched patients. They found this much more balanced, and no significant differences in these measured characteristics between treated and untreated groups after balancing using matching and propensity scores. And so they relied on the fact that in this table 1 kind of idea, that after we've matched people, we've obtained balance in measured characteristics, which is a great thing to have. And I would argue, and Bob would argue, Osfeld, that after balancing on measured covariates using propensity score methods, that there's one big characteristic that varies between treated and untreated patients. And it's going to sound funny. Well, the treated patients got treatment, the untreated patients did not. So the whole group of people who were balanced on measured stuff, and yet at the end of the day, one group received treatment and one group did not. And so why does this occur? At the least, we would argue that something has to be, something unmeasured has to be related to treatment assignment that must be different between the treated and untreated patients. Something caused, and you could argue what it is. You could argue that it's just random at that point in time. But I would suggest to you that once you start making those statements, you're bringing theory into this. You're bringing choice theory into that idea. So I argue that propensity score methods, that the source of all effect identifying treatment variation comes from these unmeasured factors, comes from the things that move around treatment choice that are unmeasured. So you should have a pretty good idea of theoretically what those things are. So in regard to other research that has tried to address this question, there was a paper by Austin in Statistics and Medicine in 2007 that used simulation models also that showed that at the end of their simulation, that imbalance in unmeasured factors after assignment remained after using propensity score methods. They didn't tell us in that about what the changes in the balance of the unmeasured covariates, but they just suggested that this remained, and that seemed uncontroversial because no one ever suggested that there would be differences between, that all balance would go away. It was unclear from the study how this imbalance was affected by the use of propensity score methods that are used to balance measured covariates. And so we realized in this paper, this research, that propensity score algorithms actually exacerbate the imbalance in unmeasured factors that affect treatment assignment. So they had to exacerbate some of the factors that related, factors that related to treatment assignment. And so our research goal was to use this a simple model of treatment choice to assess the effect of propensity score methods on the balance of measured factors that affect treatment choice. And went back to a model that we had used, a paper that we had passed out by myself and Don Fang at the University of North Carolina, where we did some simulation models to try to look at how to interpret estimates from various estimates out there when there was heterogeneity in treatment choice. But we took that model and simplified it dramatically. And in this model, we have outcome defined as someone being cured from a given condition in the simulation approach, and that patients in these models can be cured without treatment, but treatment increases the probability of a cure, so treatments are effective. Patients value being cured, but in these models, treatment is also costly. And in these models, factors affect the probability of being cured, and also they affect the value the patients place on treatment. And subsets of these factors are subsequently measured by researchers that can be used for analysis and creating propensity scores. And so in this respect, in our model, that the treatment value is essentially derived by the fact that people value a cure, and treatment increases the probability of getting a cure, and so that's why people value it. There's not an innate valuation for the treatment in and of itself. And in our model, there's a cure relationship, and all these models, like I said, are very simple, and they're linear models, where we model that the probability of a cure equals a linear function of t, whether someone's treated or not, and this xm variable, which is going to be our measured covariate, and two covariates which will be subsequently unmeasured by the researcher, x1, x2. So C equal to 1 if cured, 0 otherwise. PC is equal to the probability of being cured given treatment, the measured covariate, and these two unmeasured covariates. T equal to 1 if treated, 0 otherwise. X represents, once again, measured factors affecting both cure and treatment choice. XU1 represents measured factors affecting both cure and treatment choice, where XU2 here represents unmeasured factors that affect only the cure. When we created our simulations, our parameters in our model, the beta 0, beta t, and the parameters were specified in such a way we made sure all our simulations, everybody had a cure value that turned out between 0 and 1. And parameters BM, BUI, BU1, and BU2 represent cure probability changes associated with patients having the characteristics XM, XU, and XU and XU2. So now for this approach, for what we're going to do in this study, the valuation simulation part of this is the biggest thing that we were mainly focusing on. But we wanted to tell you where the treatment valuation comes from. So, for a patient in our simulation model, we simulated this thing called T star, which some people can call it a variable representing treatment valuation. And in our simulation, our simulated patients, their treatment valuations would vary with their values of XM, XU1. Now we've got XU3 and XU4 here, which are defined below. So V represents the assumed value of a cure to the patient. So if someone values a cure at $2,000, that's what's in here. But then V times B1, where B1 is the increased probability of a cure that you found in that our probability of cure relationship. So then V times B1 is kind of a derived valuation of a cure given V before we subtract out any kind of cost or change things relative to the other characteristics. X here reflects the treatment cost in our simulations that all treated patients pay. X is defined as above. It's a factor that affects both treatment valuation and the probability of a cure. X1, XU, and then it's measured. XU1 is just like XM, but it's unmeasured to the researcher. X3 represents factors that are related to treatment choice. In our models, what we did is we subsequently related X3 to X2. Now, if you remember, X2 was the measured variable in the probability of a cure relationship. So we are binding these variables together. Then X4 represents unmeasured factors related to treatment choice, but not related to cure either directly or indirectly. And as a sidelight, X4 would be something that an economist or anybody else would be looking looking for, if you can find things like X4, these would be your instrumental variables, things that affect the value, how much people value treatment, but don't have a direct relationship with outcome. So what we did is we assigned parameters to everybody for the valuation of a cure, the cost of an outcome, and we kept parameters constant for every patient. But we had several simulations in which we varied these parameters, and I'll talk about it in a minute, simulation scenarios. But what we did is we assigned everybody values of XM, XU1, XU3, and XU4 from uniform 0-1 distributions, and then basically calculated their T star. And we simply said that if a patient will choose treatment if treatment is going to be equal to 1 if T is greater than 0. If the net benefits of treatment are positive, then we just assumed in our simulations that a patient would have received treatment. So it means this net benefit in this treatment choice is going to vary with XM, XU1, XU3, and XU4. I think these are called DAG diagrams. And of how this thing looks like when it's through is that we have XU4, XM, and XU1 and XU3 directly affecting treatment choice, but our cure probability is affected by X2 treatment, XM, and XU1, and then X3 affects both treatment and XU2, providing then therefore a non-confounder related to XU2 also. So here what we did in our simulation approach is that 8 distinct simulations. In our simulation we had, because computers are easy to run nowadays, we had 100,000 patients received values of XM, XU1, XU3, and XU4 based on independent uniform distributions between 0 and 1. Then we calculated a new variable for XU2 to make sure that XU2 was related to X3, just using a weight of 0.5, where we create another independent uniform random variable, and XU2 was defined as being half XU3 plus this independent variation. So we broke up the relation, but there still was a correlation between XU2 and XU3. In our simulations, though, we varied. We had 8 simulations. Them varied with the value weights placed upon measured and unmeasured factors in the treatment valuation equation. So the alpha M, alpha U, and alpha U3, and alpha U4, and on the next slide I'm going to show you the values we placed on these things and the relationships to see across these 3 scenarios. Then we took one of these scenarios and we built correlation in between XM and unmeasured factors. And so, for example, for each measured factor I, XUI, we said that that can be defined as weight times XM plus 1 minus the weight plus a random component. So each EI was independent uniform random variable 0, 1, and we had 5 other, 1, 2, 3, let's see, or a total of 6. Well, we had where we varied weight. The higher weight became, the more our unmeasured variables were correlated with XM, our measured variable. So the scenarios we created, and this table, need a little drink of water there, folks. This table summarizes our 8 scenarios, where V represents we had kept a constant valuation for a cure at $1,500 across our scenarios. The probability of being cured from treatment, we have kept at a constant 0.2 across the scenarios. But if you focus on scenarios 1 through 3, you'll see that those scenarios were constructed without weights between, or without any correlations between the measured and unmeasured variables. So these are correlation-free. What's distinct about these scenarios is that the valuation weight that's placed upon the measured variable stays constant, and is moving from scenario 1 through 3, though, we see that the valuation weights that are placed upon the measured variables falls. And so in scenario 3, relative sense, the measured variable has a bigger impact on treatment choice than do the unmeasured variables, whereas in scenario 1, unmeasured variables have a bigger impact on treatment choice than measured variables. And I want to point out here that this S variable was the cost of treatment that we had in these simulations. You'll notice this varies across these scenarios. And what we did is we varied this to make sure that in each scenario, about half the people would use treatment. Just to consistent there. So as you can see, as the valuation of these factors fell, we had to lower the treatment cost in order to make sure half the people across these scenarios chose treatment. Now, scenarios 4 through 8 represent the scenarios where we made these scenarios just like scenario 2. The value weights that are placed on each of the covariates, whether it be measured or unmeasured, were the same as scenario 2, the one right in the middle. But now what we did is we applied these weights when we're computing our, and here's the, once again, the definition of the weights again down here in the footnote, where we apply these weights. And so up in scenario 8, you can see that the vast majority of our unmeasured covariates come from our measured covariate. Whereas down in scenario 2, which is consistent with scenarios 4 to 8, there's no relationship. The amount of from scenarios 4 through 8, the correlation between the measured and unmeasured covariates grows in these simulations. Okay, so then what we did is I kind of stated earlier, is that given each patient's values of XM, XU, X3, and X4, treatment value was estimated for each patient, and treatment choice was made given the criteria I described before. And then a propensity score was estimated for each patient I using a linear probability model by simply regressing the treatment choice that we observed on XM. And we've been using a linear model all the way. I just want to emphasize, this is a linear model where T-hat here represents our propensity. We've done this with logistic regression, and that doesn't change the results I'm about to demonstrate to you guys in any respects, except this is the simplest model that sticks with our simulation approach. Then, given these propensity scores, we tried 5 different ways of modifying our samples and to create balance with the measured covariate. We stratified patients into 5 bins using the algorithm described by D'Agostino in 1998, a paper that's been cited many, many times. We tried reweighting the sample using the inverse probability weighting algorithm described in these citations. And then tried matching without replacement using the propensity score using 3 different matching tolerance values, 0.1, 0.01, and 0.001. After we modified the sample, given the various propensity score approaches, in each scenario we compared the balance of both the measured and unmeasured factors that were related to treatment choice between the full sample and the score modified samples. And I can't go over, show all the results across all the variables, but one thing we did find is that for every variable in our treatment choice equation that was unmeasured, I think it's X1, X3, and X4, we found the results are very similar to this. Nothing changed. So what I'm going to do in our results is just show what we found for XU1, the first unmeasured variable, and this is the one that has a relationship with Q. So this is the big hanging unmeasured confounding variable out there. And so what I'm going to present results is the results from scenario 2 at first to try to give you an idea of the numbers we are looking at. And we're in scenario 2, and it's this scenario where there's no correlation between XM and any of the unmeasured to the researcher covariates, especially X, and this is looking at U1 specifically here. In scenario 2, there were we ended up with 50,043 untreated patients and 49,957 treated patients. And then if we look at the mean of XM in each of the patients in the full unweighted sample, we saw that untreated patients had an average value of XM. Remember, this is a number between 0 and 1. Everybody's assigned a value of this number between 0 and 1. So when we look at the average of XM for the untreated patients, it's 0.375, and for the treated patients, it's 0.627, with a difference of 0.525. Likewise, and XU1 was defined basically the same way as XM, except for this variable is not going to be available to the researcher for subsequent research. we find untreated and the treated patients have the same difference between XU1 and XM. So now in scenario 2, when we did what's being shown on this table here is when we grouped everybody based upon the propensity score band. We broke up using propensity scores into 5 groups based upon that propensity score and grouped people that way. You can see that when we cross the bins, that obviously in the bin with the higher propensity of treated, so down in 5, a larger percentage of treated people end up here. But in this scenario 2, we had plenty of overlap between untreated and treated patients in the bins. And if you look at XM, you'll see that within the bins, we see the difference doing exactly what we would expect it to do. Basically, the difference, which was 0.252 in the unweighted sample, to basically go away when we resample and group people based upon their propensity score based upon XM. When we look at the mean of XU1 across these samples, we find this going in the opposite direction. And so this is hence the kind of the story of our squeezing the balloon. And the idea here is that if you look at it when we through the propensity score methods bounce on the XM, differences between the treated and untreated patients in these groups have to come from somewhere. And they have to come from the unmeasured factors affecting treatment choice. And so you can see that the difference now between the unmeasured covariate now has increased relative to what it was in the full unweighted sample. So if we graph this, try to give you a visual interpretation where we're looking across the 3 scenarios, scenarios 1, 2, and 3, in which our unmeasured covariates had no correlation with the measured covariates. And so the green line here, the blue line here represents scenario 1, the red line scenario 2, and the green line scenario 3. The red line is the line that follows from these results on scenario 2 on slide 19. So what you're seeing, this red line and this red line up here represent values from that table. And what these are measuring, and I want you guys to note that this is the percent reduction or increase in the sample mean difference, the treated minus untreated, from propensity bending for XM and XU1 by the unmeasured covariate effect size. So what's varying here, you notice this alpha value down here as we move across scenarios. Alpha 1 is the scenario in which, I want to make sure I got this right because it can be scenario 1 in which the unmeasured covariates have a lot more variation. They're a lot stronger with respect to moving treatment valuation around. Where scenario 3 was more dominated by XM moving measured covariate, measuring treatment valuation around, and scenario 2 was right in the middle. And so what we see here, and then I also want to show that graph A is for XM, the measured covariate, and graph B is for XU. Also notice that the y-axis between these 2 graphs are different, where XM, this is a positive number representing a percent reduction, and XU represents an increase in the imbalance between the in 1B represents an increase. So the thing that we can see from here is that place when measured unmeasured factors explain a lot more of the variation in treatment choice, that it's easier to balance XM. That down in scenario 3, where the unmeasured factors have a relatively smaller effect on treatment choice, it's harder to balance XM to begin with, and you have a harder time balancing XM in the 2 tail bins, bin 1 and bin 5. And on the opposite respect, the more looking at XU, that the imbalance of XU increases, the less effect that XU measured factors have on treatment choice. And so this is a big increase down here in scenario 3 in unmeasured covariance imbalance. But they're all of these are negative. And we also looked at matching here. We did, in our results for Youre's probability weighting does basically the same thing as these results we're finding. That if we look at what this graph represents, once again, we've got percent reduction increase, and it's a little bit, maybe a little bit difficult to follow, but we have XM in figure A and XU1 in figure 2B. The y-axis in each of in figure A represents the percent reduction in imbalance for XM, where in 2B this represents basically the increase in imbalance for XU1. Some of the things to see that are interesting in here is that as the level of tolerance is bigger. I mean, we can match people when I just want to make sure I got there's numbers floating around here. I'm sure you guys have got you confused enough. And in scenario 1, where the unmeasured covariates have a very strong, they're really strongly pulling and moving people around. And when you have the blue line here, that's when it's easier to match people. Even all across in scenario 1, all across these scenarios. And you can see it's harder to match people when the tolerance falls, as you would expect. But the more variation there is in the measured confounders, the easier it is to match people. So in scenario 3, where the measured characteristics have a higher probability of have a higher effect on treatment valuation, the harder it is to find matches with people. And then likewise, you can see the sample numbers staying in effect, but also we see the same result, that the more that the measured characteristics affect treatment choice. So in scenario 1, the harder it is to match people in these results, and the more imbalance that you're going to get in the unmeasured covariates. And the reason for that is that the less and less variation there is available in a treatment choice from the unmeasured covariates, the harder it is to find enough variation to find matches with, because people aren't randomly moving around because there's not a lot of variation left over to create these matches from. So then you guys may be asking, well, what about the other scenarios where you have the first 3 scenarios were scenarios where we had correlations between the unmeasured covariates and the measured covariates. But scenario 7, which is a representative scenario, remember we went from scenarios 4 to 8, where we increased the proportion of the measured covariates that were related to the measured covariates. In scenario 7, there was 92% correlation between XU1 and XM. The interesting things to see about this, you guys may be seeing, potentially some good bad news here, that once there's very little variation in the unmeasured covariates out there, you can see that the harder it is to create overlap across propensity score bins if we're looking at here, and it's simply not possible to get the differences between groups, because there are no treated folks in the low propensity score areas bin, and there were no untreated folks in the high propensity score bins, because there's just so little variation in XU left over to force people into those bins. So, but you turn around and look at the good news, you can see that, doing this approach, we had a lot of variation. We sure enough were getting rid of the imbalance still between XM, between the treated and untreated groups. And if you look at our measured XU1, which remember, XU1 contains XM and this E thing that I described earlier, this portion of XU1 that's actually independent of the unmeasured covariate, you can say, wait a second, this looks like it's lowering the difference between XU1 between the propensity score from the fully weighted sample here and the propensity score bins. But next slide, what I want to do is this is the same information that was on the last slide, but instead of graphing XU1 over here, we're graphing the portion of XU1 that is unrelated to XM. And in that case, you'll find that actually beforehand, there was little difference in the treated, untreated patients in terms of that portion of FQ1 that was unrelated to XM. And given that unrelated portion, then we see the imbalance growing again. So kind of a lesson learned from this is that you need to have, in order to get comparisons here, you need to have independent variation in unmeasured covariates in order to generate these comparisons. But when you look at that portion of the unmeasured covariates unrelated to your measured covariates, you still find the increase in imbalance, or you still find the squeezing balloon effect. I just want to, this is basically the scenarios looking at XM and E, the portion of the unmeasured covariates that are unrelated to XM, and you find we find basically the same kind of results that we found in those earlier graphs, except you'll notice that as that portion, as we go from scenario 2, which is the blue here, down here, this little dot, which is scenario 8, which was very high correlation between XM and the unmeasured variables. It's very hard to find people you can't find people in the tails to match anymore. And actually in scenario, in scenarios 6 and 7, we lose bins 5 and 6, for example. And probably too much information to go through here, but the same results apply. With this type, we are looking at the matching. So let me jump down to the conclusion that we reached from this study. And the conclusion is a relative term, because and I'll show you on my last bullet here. I think it's definitive, though, that we find that propensity score algorithms require variation in unmeasured factors related to treatment choice that is unrelated to the measured factors. You need to have independent variation in something to cause people to make different treatment choices after controlling for measured factors. Our results suggest that forcing the balance of measured factors affecting treatment choice using propensity score algorithms, though, creates more imbalance in the independent variation in unmeasured factors that affect treatment choice. And so the whole idea from our first bullets in their introduction that if you find table 1 measured factor balance, that actually has the opposite implications relative to unmeasured factors between randomized controlled trials and observational studies. They mean different things. If they're balanced in a controlled trial, that's just saying that your random number generator balanced measured things, more likely it balanced unmeasured things too. But here, if you find balance in measured things, it's just that the unmeasured things have to be more balanced in order to have people make different treatment choices. And so then, therefore, the need for theoretical justification that unmeasured factors affecting treatment choices unrelated to outcome is even more acute, we would argue, in propensity score-based analysis than approaches using the full patient sample, because you may have you will, according to the results, exacerbated the difference in the unmeasured factors. But there's one simulation model. It's a very simple simulation model, a very straightforward simulation model. We challenge researchers to try to find scenarios in which unmeasured factors that have a direct effect on treatment choice become more balanced using propensity score algorithms. And there's our references, and I'll be glad to take any questions that folks have. Much Liz, how does
this guy went to MIT, and
one's unmuted now.
This website where he teaches, it's geared to like high school-ish kids about complex concepts. And so it started with him teaching his cousins how to do like math or something like that. And then it got the attention of Bill Gates, and he's like now, and it's like a really awesome thing. So the reason, like, I need him to like teach me how to do propensity. He has like videos, and it's like amazing because he like teaches him every video by
Everyone
himself.
know that they're unmuted.
Probably 1,000 videos.
Can you mute, please?
On everything from like algebra 1 to art history to like organic chemistry. Yeah. I mean, people majored at MIT was like this.
So, John, can you hear me?
I hear you.
Okay, great. Sorry, so somebody is on this line is lecture about something else, obviously. But John, so great, you brought back the conclusion slide. I want to open this now to any questions, and I'm hesitant to ask Liz to unmute this, so if you can type any questions into these Q&A field, and then we read that out. Any questions from within this room here, and also before, while people are formulating their questions, what specific recommendation would you have, John, based on these conclusions that you list on your slide number 26? What is now the best strategy to model this? Do you want to have less parsimonious models just in order to capture as much unmeasured confounding as possible, as well as proxies for unmeasured confounders? Or rather want to see more theory, if you have the luxury of being able to develop a theory, and just make sure that all the important confounders are in your model?
I think that's the kind of the lesson, and it's funny, Sebastian, just the other day I was working with Betsy Crescelis, and you know Betsy, and hopefully lots of folks out there know Betsy, about a project where we were looking at the use of various types of chemotherapies for patients with non-Hodgkin's lymphoma. And we reached a scenario where there were a group of people that got no chemotherapy at all, and then there was a group of people that had rituximab and very, let's say, chemotherapy light, not the real strong stuff. And I said, wow, there may be an opportunity for these people who got no chemotherapy to get this chemotherapy. And then we were comparing patient characteristics between them. So we said, oh, those are imbalanced. And I found myself saying, to make a fair comparison here, try to find a way to balance it. And I went right into a propensity score mindset. I had the oncologist in the room who said, wait a minute. At the end of the day, aren't these people still different? But it was kind of a nice, but we started talking through then all the various factors that would be related to the choice of chemotherapy or not. I think that for definitely methods, you could feel the value of trying to make sure that when you're making comparison, that everything is even. The other side of the coin is you're still left with, why are they uneven? Why did they make different treatment choices? And so that's, I think it goes back to, I think we should all be talking about, to begin with, the theory as to why we think people did different treatment choices. And so we can discuss whether the factors that could be related to that theory really are a counter or not. So that's kind of the lesson that I take from the result we found here.
This is in a cautionary note of not over-interpreting your table 1 after propensity score matching. Yeah. Perfect. Yeah.
And nice if people, I think, went into a models, when you're using observational data to compare outcomes, went into that discussion to begin with a theory as to why some people are treated and some people are not. Because then you have a discussion about the things that are measured and the things that are unmeasured. And then that just frames your discussion section at the end, the limitations of your results.
All right, so I have a question here from Alan Ellis. It's okay. Thanks for the presentation. The findings generally make sense to me. I have 2 main implications from this. 1, we should do the best job possibly of measuring important confounders based on theory. And 2, it's appropriate to do sensitivity analysis to show how unmeasured confounding might be affecting the treatment effect estimates. Any comments?
I guess we do that. I mean, we can take observational data, right, and pretend like and give variables that we can measure and then drop some. See how and assuming that this is unmeasured, and then we can add them back in later and see how our results are affected by that. But and I know that you guys, Sebastian, you're all stuck at the end of the day that you can spend a year finding every single measured variable that you possibly can, and at the end of the day, as long as your R-squared on your propensity score treat not 1, or however we define that, there's still things that are up there that are affecting treatment choice. Yeah. Still have to have theory about what those are.
Right. Actually, John, we sometimes see the flip side of what you described, which is when we have a set of, let's say, 20 predefined variables that all agree are probably important confounders. And then we had hundreds of empirical covariate that our HTPS is identifying as potential confounders. We match all that, right? We see actually that we see some sort of increased imbalance in these predefined covariates as compared to matching only on the predefined covariates, right? So something's got to give. But all, I would think that the validity is higher in the non-parsimonious models. Don't see that reflected necessarily in a more narrow table 1.
But you do worry, though, if you kind of one of the lessons here too, Sebastian, is the fact that if I know you guys have done the high dimension, is that what the high dimension propensity score methods, that if you put too much in here, I mean, at the end of the day, you really get a high, for lack of a better term, a high R squared on your propensity score method. But the higher you get that, so let's take it to the extreme. If you were able to perfectly define treatment choice, you could never do propensity score analysis because you can't compare there's no treated and untreated people left. It'd be a perfect determination, right?
Clearly, clearly you want to do this with factors that are predictive of outcomes, not just exposure, right? A question by Eric Smith, lots of questions, still not clear why unmeasured has to increase. Would seem to suggest propensity scores not counterfactually valid. Also, William holds in non-propensity score models a logistic or linear regression with these factors. So is this specific to propensity scores, or is that for a regression model?
So could you get, what was the first part of that question?
Still not clear. Unmeasured has to increase. Would seem to suggest propensity score not counterfactually valid.
I think propensity scores can be valid as long as you're willing to make that first assumption that everything that's unmeasured is irrelevant outcomes. There's wrong with that at all. But you can't go into this theoretically. You have to make a statement about what's unmeasured, and so I've been kind of hesitant to talk about that. But in years past, I was actually somebody called me a bad word for asking this question at a conference one time. Where I asked a panelist if you've got two people that have a 0.7 propensity score based on characteristics that are identical. But what's different between them is that one person was treated and the other person was not. And so I said, well, why did that occur? Kind of asked that question in the slide. And the analyst said, well, maybe one doctor had a flat tire on the way to work that day and the other one didn't. But I would add that therefore, if we measured the variable, did your doctor have a flat tire, there's more imbalance in doctors having a flat tire between the treated and treated group. The that affected treatment choice, the theory that this suggested that it was the grumpiness of the doctor that affected treatment choice. And if that doesn't affect outcomes, well, then that's a valid reason for why two people with the same propensity scores would not be treated. And that would be a valid reason as to why the estimates that you get when comparing those two people, it would be a good estimate. But you have to have that theory to say why someone didn't get treated and someone didn't. And you have to have that theory whether you're going to do logistic regression or any other kind of regression. Anyway, so kind of here is you're not getting out of theory.
Right. And whatever you said is actually not specific to propensity scores, but propensity scores are a nice model to illustrate these things, right? But it's not limited to propensity scores.
And the second part of the question, I'm sorry.
We asked actually Liz to unmute for everybody now. We'd give it another try, and maybe if Eric Smith is on the line, please, if he would speak up.
Okay, I am. Yeah, I'm on the line.
Perfect. We hear you.
Actually, you've answered my question very good, except the last thing I would say, which I think is getting to Sebastian's point too, the challenge that we face, John, or the challenge that I face, and Sebastian's written about this elegantly, is I would maintain it's almost impossible to theoretically identify what your true confounders are, sort of from health databases. They're just too complex. You can identify maybe 20 high priority ones, but you can't identify all the rest. You need some sort of empirical strategy. And my question is, okay, what I'd like to see represented is, okay, your unmeasured confounding increases, it becomes more imbalanced. But what about the aggregate explanatory power of your model to sort of eliminate the total amount of measured plus unmeasured confounding?
Well, Eric, when we did these scenarios, we found that, I guess the key wasn't the total variation described; it was the portion the portion described measured. So as the measured variables describe more variation in treatment choice, it became tougher for the propensity score methods to find matching people. It became tougher to find. Our bins our bin 5 and bin 1 became smaller because we couldn't match people there. Well, no, the bin size didn't become smaller, but the comparisons in those bins became smaller because the more that we describe variation, the less extra variation that was out there to cause people to make different treatment choices. And I guess I want to make a distinction. Also, Eric, you mentioned about identifying. I want to take even a step back from there, and I think researchers should theoretically or conceptually identify they affect treatment choice and have that laid out first, then stop and say, from among those factors, which can we measure? So you mentioned 20. So if I can come up with conceptually 25 different things that I think affect treatment choice, and I can measure, get a measure of 20 of them, well, at the end of the day, you can say, look, there's 5 things out there that are affecting treatment choice, and you can either make the statement that I don't think any of those 5 things have a direct or indirect effect on outcomes, or you can say, then you can do the work by saying that maybe we can bound our outcomes given those unmeasured things. But that whole discussion relies on somebody a priori defining what they think and having your reader accept what you thought your theory was about the things that affect treatment choice. But, that's just coming at this as economists, where we just harp on that kind of stuff, and I've got it from pharmacoepi friends that maybe I spend a little too much time thinking about those things, but that's our point of view. Maybe there's some kind of nice meeting place in the middle.
Sebastian, I'd like to ask a question. It's Lisa here.
Go ahead.
Okay. I was thinking about our data. I'm at Kaiser, and I'm thinking about our data and some of the crazy things I've seen in our data. And, there are a lot of things happen in a data collection system that probably don't have anything to do with the outcome. One department does a better job of recording things than another. Over time, things might shift. A system will change. A data collection system will change suddenly in one place but not the other. And if you don't know about that, you might just use data in a naive kind of way. The thing that I have noticed is that if you've got a short period for identifying the outcomes, if you're only pulling the outcomes out for 1 year, for example, the timing that the outcome is recorded can really be influenced by these funny little things that happen in the system. The longer you have to watch the population, the more confident you can feel that the outcome is a genuine outcome, or that being recorded, less in a timely way. Mm-hmm. But what I do see is that if you're only looking for 12 months, whether a patient gets it recorded this month or next month can really be related to other aspects of the measurement system.
And I mean that would definitely increase standard error. I mean, if your outcome is measured noisily, the more noisy it's estimated, which one of these methods that you do, you're going to have problems coming up with significant estimates at the end if there is truth out there. That's true. And who was this at Kaiser? I'm sorry.
Harrington.
At least I'm sorry. I touched that. Okay. And so, but Lisa, but it doesn't. That also depends on what type of condition. If someone has an acute condition where I need to be cured by an infection in a week or something like that, length time is going to be the vast time is going to be a function of the condition you're looking at, right? So,
I think you're saying that what the concern I just raised is general than this propensity score issue that you're talking about.
But a good one.
It's John Seeger, and thank you for the very thought-provoking presentation. It is occurring to me as I was listening to you that some of the things that you were describing will be even more acute when you do, depending on the level at which you do the propensity score type analysis, or that is if you're looking, say, if you do it conditional on the individual prescriber or on an individual institution, that these kind of issues are likely to be more acute because the prescribing by an individual prescriber might follow a very systematic algorithm, or even within a hospital, the choice of one therapy over another may be subject to an algorithm. When if you combine across lots of prescribers or lots of institutions, that the variation in the separate algorithms that each of them employ, they come down to things that may not really impact the outcome, so that this assumption that it's a random effect that's leading to the variability in exposure may be more justified. Anyway, just a thought. Any comments on that?
Interesting. So then, can anybody still see the slide? I'm not sure. Back up to. So this is the treatment valuation equation, and just assumed everybody out there has the same alpha parameters in this thing, which is just, the random number generator gives you an XU1 of 0.34, and then you get multiplied. Everybody gets multiplied that the same parameter, and I guess you could think of scenarios maybe where half the population alpha U1 is a positive number, and half the population alpha U1 is a negative number. And I'm wondering, it's just hitting me that maybe that's one create noise. I don't, but I guess there may be a way to try to get at this. What I'm saying, even if you did find that, so you told the story, you told a theory, and so I got all these data the data from this larger groups of not just one hospital or one doctor's office, but many doctor's offices. You have to tell the stories that the things I think that are measured here. So let's say that in these simulations, half the people alpha U1 is negative, half U1 is positive, and we find that balance goes away, for example, that the score things also balance this, or it has no effect on the balance. But then you'd have to. That's a very specific scenario that your theory would have to match. Tell a story that XU1 affects half the doctor's offices one way, and the other half the doctor's offices another way. Yes.
Any more questions? Does it all make sense to everybody? Can you link these theories to this in your minds? And if not, please, just your last chance to speak up, get in touch with John here. Otherwise, I can give you his cell phone number later for any follow-up questions. But
this paper, there's a paper under review at Health Services Research right now, so that's why I wasn't able to. I don't know whether I can send papers out. I don't know how that works. Whether HSR would be mad. There's the do not quote stuff down at the bottom.
Right.
I don't. They'll probably turn it down, but.
Chance. Any more questions?
This is Eric again. Can I make a quick comment?
Yes, please do so.
I don't know if this would be helpful or not, but maybe one way of looking at this, John, is Alan Brookhart and Sebastian of others have written about how you don't want to put in variables that are associated with treatment choice, but not with outcome in your propensity score. One of the rationales for that has been that it increases your variation, but it almost sounds like from your work that there's a second rationale, and that is whatever you leave out of the propensity model is going to become more imbalanced. And it seems like there's a direct sort of theoretical interest in having what becomes more balanced, stuff that's unrelated to outcomes.
That's good variation in treatment. That's what you want to exploit at the end of the day, and that's what instrumental variables does is try to find that good variation in treatment that exploit. That's a great point, Eric. Appreciate that.
Right, but the increasing literature, there's a paper by Jesse Myers in AJE just in a couple of issues ago, that you don't want to include variables that are predictive of only, but not of outcomes in any of your regression models. And that's not limited to propensity scores, right? I mean, it's a generic modeling issue. And I was then asked by other colleagues in the epi department, so what's new? We know that for ages. Don't do that. I think the new thing is that you have to realize in empirical studies, you will never know whether a variable is an instrument or a confounder. Otherwise, some extreme situations you might know if physical validation was involved, right? But you don't know for sure. And then the real question is not to be, right on your principles, but in empirical situations, maybe it is better, when in doubt, to adjust for these factors, right, than leaving them unadjusted, right? So the net bias is actually still in your favor. Right, it's kind of the link between theory and practice. What do you do in practice when you don't know for sure what the characteristics of your variables are?
Well, if you put in, so at the extreme though, and you put in, if you did it for randomized, if you put the coin flip for randomized studies in there, I mean, I don't know. I mean, I don't know if you can make that case in all cases though. If it's a general statement. If I'm taking the things that I really do think supports random variation in treatment, and I specify that, then I'm losing variation that I would want to exploit. I'm sorry, Sebastian, I should go finish up here.
Sure. No, that makes sense. All right, great. So we are a few minutes past 4. We started a minute late. So thank you very much, everybody, for listening and linking in. Again, we have interesting topics lined up for the next few months. So I hope to hear you soon again.